Thank you, Julian. I'm really excited to see such a great interest into this webinar. In Germany today, the Cologne Carnival was kicked off at 11 this morning. But we will see that teaching design of experiments can also be a lot of fun. So welcome everybody. I assume you already know that you can learn from your data much more effectively and efficiently than using trial and error or one factor at a time experiments. The better approach is a statistically designed experiment, or DOE, which is also supported by JMP as one of JMP's application areas. And as you can see from our customer stories, click on Design of Experiments, JMP is also a leader in industrial experimentation. However, the most important part in our session title today is teaching. So I will neither introduce you to the theory behind DOE, nor will this be a JMP how-to seminar. Instead, I want to inspire you about how JMP can be used in teaching, and I want to do this by giving you several demos, which you can either watch from a lecture's or from a student's point of view. So you will see live demos using classical and custom designs, but also some advanced or modern and special purpose designs. Before wrapping up today, I'm going to recap some tips and resources. And as always, you can easily follow all links by downloading this JMP journal from our academic webinar library. You find at jmp.com/academic, scroll down or go directly to jmp.com/teach and then choose academic webinar library. So while you are not posting any questions into our Q&A chat, it's time to lay back and to enjoy the demos. Okay, so where to get started? Now I'm a student or a researcher. I just installed JMP Pro 13, which comes by our local campus license, and I can't wait to design my first experiment in JMP. So browsing the menus for the first time, maybe the JMP starter sounds like a good starting point. So the JMP starter gives you a structured menu and structured access to different categories and all the platforms in JMP. Basic ones, fitting models, predictive modeling, other modeling, screening, but also DOE. And this gives you a structured overview about the JMP DOE platforms. So it starts, for a good reason, with a custom designer. We will see that later on. And Augment Design, you see two platforms for working with definitive screening designs. We will also see in a few minutes. Then we have some classical design approaches and the platforms for that, design diagnostics. And then some special designs for consumer studies, but also some special purpose designs, including nonlinear designs. So you can click on a button if you're interested in screening designs. Maybe you want to start with a fractional factorial design, choose screening design, set your response and your factors. So here I add 5 continuous factors. I'm just curious what happens and what I get. And then this is what you get, a list of designs you can choose with increasing number of runs. So with 32 runs, you get a full factorial design, and then with less runs, fractional factorial, Plackett-Berman, and then you learn less when you reduce the number of runs. So that's just browsing around and being curious, but how can I create my first design in JMP? So hitting the Help menu, a DOE tutorial catches my eye. So let's have a look. So, here we seem to get to the custom designer in the first place. And there are some good reasons you can also read about on the left. So there's some additional instruction and information, background information on the left, which is just provided by this tutorial. But here you can read that this custom designer is an all-purpose tool and it is useful in most situations. And it creates an optimal design. So this is created by the computer, and I could also end up with a classical textbook design, but I don't need to worry about all the bells and whistles of different design types. And if a better design exists, the computer will find it based on an optimality criterion. So this is also described on the left and can also be set on the red triangle. But no worries again, so here we ask JMP to recommend the best optimality criterion after we told JMP what we want to learn from our experiment. So I start with this tutorial, I click on next topic, and this is to define the response. And then I double click the response name, and I say I want to have yield as my response, which should be maximized. Okay, so let's collapse this. What's next? Okay, we have to define the factors. And this experiment has two continuous factors. So I add the first one, and there's a name which is die position. And die position goes from 120, low level, to 140, the high level. And there's a second continuous factor, which is catalyst, which goes from 10 to 20. Okay, these are our two continuous factors. So what's next? Define the model. So I click continue. We don't have any constraints here. So the model is what we want to learn from this experiment. It's the assumed model we want to learn about. And here we have our two main effects and an intercept I don't worry about. And I click on response surface model to add the other second order effects. One interaction, die position catalyst, and two quadratic terms. Okay, so that's what I am interested in, the model. So what's next? The run budget. So how many runs can we afford? How much time do we have, or how much money to run all these tests? And here in this situation, JMP says, okay, we need at least 6 runs because we have to estimate 6 parameters. So if you look at the model, a default, that's a best practice. The recommendation is to use 12 runs, but we are a bit limited, so we want to reduce this to 10. And then I click Make Design. Now JMP, so the computer with JMP creates a custom design for us, and this is the design. We see the 10 runs and then the two continuous factors set at their low or high levels. So we can also look at the design evaluation, and that's a good idea indeed. So here we could, for instance, see the prediction variance profile. So this design will be an eye-optimal design, so it will minimize the average prediction variance. So here, this average of this prediction variance should be minimal at the end. And here we can see that the variance goes up when we move to the borders of our design space. And that's for both factors. So that's the prediction variance. By the way, if you're interested, hey, what is this prediction variance profile? You can go to the Tools menu, get the Help tool, or just press question mark, and then click on what you're interested in, and then you get explanation about this and what you see and how to interpret the jump output. And there are also some technical details. So if you're interested in the formulas and more technical content, you can even go down and dig deeper and read about all the details and how this is calculated. So there's also a surface. So this is a two-dimensional design space. And you can also look at the prediction variance as the third dimension over a two-dimensional space for catalyst and die position. And the design diagnostics, this tells us that this will be an eye-optimal design. So next topic, so what's next? So we checked the design, we looked at some evaluation output. So now we are ready to run the experiment. Sorry. And for this I just scroll down, and then it's a default to randomize the runs. What's a good idea? And then I click on Make Table. And this is a basic table you get, a design table. So here you see the randomized runs. So this would be, the order would be random. Also the design itself can be random because there's a random search for the optimal design starting at a random point in the design space. So we see how to set our two factors per run, and then there's an empty response column to be filled after the measurements are done. So now I don't want to do this experiment, so I could use the script, which is also provided by this tutorial, but another option is to tell JMP that with the design table, I would also like to get some simulated response values. So if I make the table again, I get the same table, the same runs or similar ones, it's random. And then the yield column is already filled with some simulated values. And the nice thing is here we can determine the size of our effects. So here if we see 1, this means if die position changes this factor from low to high level, then our yield response would change by 1 unit. So all these effect sizes are the same. Also the error variability, it's all the same level here. So I could say, okay, but the interaction is really significant, and also the quadratic term for catalyst is more significant, more active than our other factors. And with this I could click apply, and then with the random error, JMP would create simulated response values for us. So I just remove the simulation tool here, I close it, and then each design table in JMP has a script DOE dialog to go back to the DOE dialog if you want to change your design, but also a script to go forward and start the analysis. So now we have our response values simulated, but good enough for this demo. So now I can run model to start the analysis. Yeah, we see the effects are configured automatically. So that's for a response surface model. We see the main effects and then the second order effects, including the quadratic ones. And I don't want to use yield here, but our simulated one with the changed effect sizes using the simulator tool. And now I click run, and then we see the actual by predicted plot. We see the effect summary, and indeed the interaction turns to be out the most significant effect, and then catalyst is second place, and the quadratic term for catalyst third place. So this is maybe interchanged because of the error, the random error we have. And I can scroll down, and here we see the parameter estimates. So these are the estimated parameters. Yeah, remember for this one I entered 3, and here I entered 2, and the others were expected to come out as 1. But there's a standard error, so we get different estimates, and you also see the significance by p-value. Okay, I close this report and this demo. So the analysis part is also explained in this tutorial. And this was actually more than just a hello world and get started. But it's easy to get into the flow when you use JMP. As you saw, a JMP design table is a central element. It is the output from our design, and after adding the response data or simulating response data, you are all set to launch the analysis. So let us look at another design file from the sample data. And there are many you can choose from. If you open help sample data and then design of experiments, you see that there are many files you could look at, and the one I want to use is this bounce data file. So this is a sample data file. It's from a design phase using a JMP designer. So here we see that this is actually a box-Behnken design, so a response surface design. And if I'm curious how this was created, I can go back to the DOE dialog. We see the response goal, stretch, and this should match a target, yeah, at 450, so the middle there. And there's no model configured here, no assumed model, because box-Behnken design that tells JMP what we want to learn about, a response surface. And design evaluation has again a lot of information for us, and one type of information is the color map on correlations. So here you can investigate the type of confounding you get. So here we see that there is no confounding or aliasing between our main effects, between each effect with itself, of course. So they are 100% correlated, but no correlation between a main effect and a two-factor interaction. Then they are completely confounded with cubic effects again. So here we see that the correlation is 1. So that means if you see that silica seems to be active, it could be silica, but it could also be the cubic effect of silica. But in many cases, maybe you can exclude and assume that a third order effect is maybe not significant and can be ignored. So back to our design table. So here we see the columns, stretch is our response, and there are some properties added to that one. Let me close that one. So we have the same here with the stretch values. So there's a property response limits, which is automatically set. So this is what was configured in the first step to match a target. And then we also have the settings for our factors. So we see that there's some factor coding applied, and this is a continuous factor which is easy to change. Yeah, so nothing what you specify during the design phase gets lost from one phase to the next. And you can always go back and forward in JMP. So you're very flexible there. Then there's also a pattern which tells you is it a mid, high or low value for our three factors. Yeah, so here to build a model, I could choose from our Analyze menu and then Specialized DOE models, fit, two-level screening to build a model. And Stretch is our response, and Silica, Sulfur and Silane are our factors. And then I use the screening platform in JMP, which tries to test all the possible effects and interactions, cubic terms, and this is a saturated model, so there are no degrees of freedom to test for error, and that means that you cannot use standard statistical tests. In this case, the Lens method is used to calculate a pseudo-standard error. Maybe you heard about this in statistics, but you don't need to worry about all of this. JMP simulates some p-values for you, and they are used to pick the significant effects and add them to the model. So if you go with a selection JMP made using this simulation, you can just click on Make Model, and then you see that the significant effects go in here, and then you can click Run, and this is the output. So here we see the effect summary. So an interaction seems to be most significant for this model, and then if you scroll down, you can also see how the model works and what the nature of the relationships is for all your factors. And we see that we have some curvature here for silica, but also for sulfur. And we have indeed a strong interaction. So that means that the relationship between our stretch response and silica heavily depends on the setting of another factor, which is sulfur in this case. Yeah, and the goal was to match this target here, which is 450. So you try to do this manually, or you ask JMP to maximize the desirability, which means find the best settings. And here you see the best settings to get a stretch of 450, and you also see the confidence interval. Okay, let's close this example as well, and let us move on to the next section and look at some classical designs. So when you want to teach the foundation of DOE like a continuous response, one continuous response with one categorical factor, this would lead you to a one-way ANOVA, and here you won't. And then if you want to teach this, the basics, you won't start on a green field, of course. So one option is to use self-paced, web-based training from SAS Education. And let me show you where you can find it and what's offered. So here, if you go down, look at e-learning courses, and then you see that there are several e-learning courses, one about classic design of experiments, and you can see what's covered in that course, and this is about, needs 16 hours to work through the content. Forget about the fee, because these courses are included for free in a JMP Academic Suite license. So from there, or also from a trainer kit, by the way, you can also request the training content, the courseware with all the data sets, the journals, and the course notes So by the way, here are the course notes. They are called trainer kits, so you get the complete package. And here we see that there's an example explained. It's about randomized design. It's a drill tip example. There are 4 different drill tips, and then we measure the hardness for these different drill tips, and here you see what this example is about. So it tells you about the factor, one factor, the experimental unit, a metal sheet, the treatment, and then the runs. So you can use this as an example, a demo, or as an exercise for your students, and then get all the data, and you also get a journal like this. Let me click here. Close it. So that's the first chapter, and then the section about completely randomized designs. And here's the data set, which is also described in the course notes. And then you can go from here. So click on DOE dialog again to see how this design was created. You see it's a randomized run order, of course, with 16 runs, but we have 3 replicants. Yeah, so we have 4 times 4 treatments, so 4 possible treatments, and then each one applied 4 times. So I could also explore this data maybe using the graph builder. So I can look at hardness by tip type, hardness in here, and tip type in here. Sorry, I need to go to the complete data set, this one, and then do the same for this. So hardness, now we get the simulated response data, which comes with the data set. I can look at this by tip type, and then maybe look at a box plot and add the data points, and then I'm done. Yeah, to see if there are significant differences in the mean hardness for our different tip types. Another option is to use fit y by x. So here again, hardness is the response, tip type is our factor, okay, and then we get this, the same plot basically with our data points. We also see the ground mean, that's the horizontal line, and now I can add means ANOVA, so means diamonds, so we see the group means, the middle lines, the long lines, the green ones, and then we also see the confidence intervals, 95%, and some overlap indicators to check for significant difference between the means. If you're interested in that, by the way, you can also compare them, maybe using a student's t-test. So this would not correct for multiple comparisons. And false discovery rates, so that's the risk here, of course, but there are better approaches for this. So one is maybe Tukey-Kramer's honestly significant difference test, and then you see the power, that there's less power with that test, and you can click on a circle and you see if the colors are different, then the means are significantly different. And the answers we get from these 2 different comparison tests are the same. And if you scroll down, you see all the means, the data, the standard errors, confidence intervals. You also get other information, maybe like this connecting letters report. Maybe you are more used to look at that. So that's all provided down there, but the most important message is given by a visual output using the comparison circles. And of course, you also get this analysis of variance output, the standard output, so with the treatment effect and then the error, and then you see the degrees of freedom, sum of squares, and then mean square, which is sum of squares divided by degrees of freedom, the F statistic, the mean squares divided, and then for this F statistic, which is quite high, we also get the p-value, which is quite low. So that means we can reject the null hypothesis that there are no differences. So there seem to be some differences in our data regarding the group means. And what about assumptions? So if you want to check assumptions, you can, for instance, save the residuals to your data table. You can save predicted values to your data table, and then we see that they are predicted here. You can analyze the error, that's this one here, using the distribution platform. Ask for normal quantile plot. So here there's no evidence to say that the error is not normally distributed. So what's good to know, so that's actually one assumption we made for this ANOVA output. And by the way, if you're interested also to teach ANOVA regression, so there's also a recorded webinar by my colleague Ruth Hummel you can find and watch online. Okay, let me close this and move on to the next example. So this is actually from our course collections. So if you go to jump.com teach and then click on course material library, you get here, and then course collections, and then you can choose type of course, design of experiments, and you see a collection of different types of material, including webinars and textbooks and e-learning courses, but also some shared material from other lecturers and professors. So for instance, there's a set of 40 videos from Phil Ramsey, who teaches DOE at the University of New Hampshire. And one introductory chapter from his course is about interaction effects in factorial experiments. So with a case about breeding shrimps. And you can also get access online to all his data sets and examples. So let me open his data set here. So here we have 1, 2, 3 factors. And the response is the weight gain of our shrimps. And the question is, how can the weight gain be increased in the best way? With what temperature, density, and water salinity? So that's the question here, and the factors are coded as continuous factors. So I can also use the distribution platform to check what we have here. So we have 3 levels for salinity, and we have a low-high level for water temperature and shrimp density, which can be seen here. So if you're interested in interactions, if you assume that there could be maybe some interactions, you could also try to answer this question during your exploratory steps. Maybe you look at Graph Builder and then you look at the response by temperature. Yeah, and then you see that there is an effect of temperature, but if we overlay this with salinity, we see that, for salinity 10, which is the low level, there is an increasing effect, and the other two, at other salinity settings, the effect of temperature is decreasing weight gain. So that's interesting. Let me close the Graph Builder again and build a model. So there are also other outputs. So this one is an example here. So we see weight gain by salinity at different temperature levels. And that's interesting because at high temperature it's almost linear, but at low temperature salinity seems to have a quadratic or at least a curved effect. And that's possible because salinity is a 3-level factor and can have some curvature. So let me fit a model here, and here we see the result. So can look at the effect test, and all these effects are significant, and the quadratic term for salinity is highly significant. And then there's the prediction profiler again. That's the standard profiler I can look at, and here we see the same interaction again. So remember, at low temperature salinity has this curved relationship with weight gain, but at high temperature salinity has an almost linear effect on weight gain. There's also an overview, especially if you have more factors you're investigating. You can also choose an interaction profiler or interaction plots, and then you see the same information again. So here we see the relationship between weight gain and salinity depends on temperature. So we have the two curves for low and high temperature. And with each model you build in JMP, you can save the prediction formula, the model formula, maybe to your data table. And then if you do this, you get a new formula added, a new column added, which has a formula, so that can be seen by the plus sign. So this is the formula of our model. You don't need to worry about. You can see how this works using the profiler, but this can be used for prediction. Or you can also use the surface plot and then take the formula, and then you can look at the surface plot. So here we see the predicted weight gain by salinity and temperature. And again, if you look at low temperature levels, we see this curve here, which has some curvature. And then if you look at high temperatures, we see the curve here, which is more linear. Okay, so let me close this and move on to the next section, which is about custom designs. So while the classical designs we saw so far are helpful in teaching basic concepts, they are not really flexible enough in most real-world situations. So therefore, experimenters in industry prefer the custom designer to get the optimal design for their specific problem. So let me show you some options during the step-by-step creation of a custom design for tasting wine. And this is an example you also find in the Design of Experiments guide in the documentation. So a factor table can also be found in the sample data. So here we see the factors. So there are two varieties of wine. The wine can come from 4 different fields. All the factors are categorical. We have 2 types of yeast and low and high temperature and so on. And we will have 5 raters or wine experts, each of them tasting 8 wines. So that's what we thought about the experiment and what we could do. And the question is, which type of wine our raters like most on a scale from 0 to 20. So let us start from scratch using the custom designer. So the response is rating for our wine, and we want to maximize, the higher the better. And it's between 0 and 20. So we also assume that responses of one rater are more similar than responses between different raters. So this variation can be purged by adding a so-called blocking factor with 5 levels. So since we are not interested in generalizing to a larger population of raters, we can add a fixed blocking factor from this menu here. So I choose add a factor blocking, and then each block is one rater, and each rater should get 8 wines. So I choose 8 runs, 8 wines per block, per rater. So all the other factors can be loaded, so you can, after configuring factors, you can save them. Now I have a factor table already open, so I can load them in here, and now we have all the factors imported from our factor table plus the blocking factor called rater. Okay, so we don't have any constraints again. The model is just about main effects, what's fine, and it's necessary to estimate all parameters. So that's good. There are some alias terms. So these are terms not in our model, but they will be analyzed for aliasing with the terms which are in our model. So that's quite interesting information, diagnostic information we could get. And here the suggested number of runs is 16, but we have 5 raters, 8 wines each. So that means we want to do 40 runs. And then JMP knows with 8 wines per block. So then there are 5 blocks with 40 runs. And that means 5 raters. So that's what we want to get. Yeah, if you really want to reproduce a certain design, because the custom designer has a random result, basically, you can do this by setting a random seed. And I do this now to show you how this could be done. So set random seed, and here I type in this number. And JMP uses a coordinate exchange algorithm to find the best, the optimal design, but starting at a random starting point. And this defines the starting point, and with the same seed, you start at the same point, and then you get the same result at the end. So that's especially useful in teaching when you want to ensure that all your students get the same result. And now I click on Make Design. And we see the design. I could look into some evaluation output, especially maybe the color map on correlations. And we see that there are some correlations, not between our main effects in the upper left corner, but elsewhere. The main effects are fine. They are all blue, orthogonal, and they can be tested independently. So that's good news here. And then I make the table. And this is our design table. Yeah, I close this one because I have the same table here. It's also included in the sample data. It's the same table now, the same design, but it has the ratings filled out in the response column called rating. Yeah, and now I can build the model. I just go immediately to the reduced model you can get by reducing effects from the effect summary interactively, and this is the model. Yeah, and we see that yeast is highly significant, most significant in our model, then D-stem and filtering and so on. And rater is still significant, but borderline significant. Yeah, you get some diagnostic information, but again, you get the profiler output. Yeah, and here the question is, so how to get the best rating? You can set all of the factors to the highest points, but again, I can ask JMP to optimize this, and then the best rating is for this wine here. So with cultured yeast and air barrel seasoning and with filtering, used, and that's the best wine, and we can expect an average rating for such a wine using our raters of 19.9. That's quite good. So 20 is the maximum here. Okay, so let me close that one as well and show you one other example which comes from a book. So there's also a list of tips, but this is more a reminder for you when you download the journal, and there are some resources listed you can check out when you get the journal. And here's the book where I want to show you a case from. The book is from Brad Jones and Peter Goose. It's called Optimal Design of Experiments, a case study approach. And one case study is about a wind tunnel experiment. And in this case, there are some hard-to-change factors which are best implemented using a split plot design. And here is the design table. So I click on DOE dialog to check how the design was created. And this is real world now. It's a case study from the real world. So there are 100 random starts, 130 searches in this case actually, to find the best design. And this is the best design which was found. So we see the design here, and I can go back. So we see this experiment has 4 responses. 3 should be minimized and efficiency maximized. But here's the point. So these are our 4 factors. But 2 of the factors in this wind tunnel experiment, the front ride height and the rear ride height, they are hard to change. Changing them requires to shut down the wind tunnel, which takes maybe half a day to reconfigure everything and start it off again. So these factors are configured as hard to change. And this will tell JMP to create a split plot design for you. So let me close this one. You can evaluate the design at any time. So now we have a better setup. Our runs are not completely randomized anymore. What's easier for us, we can save a lot of time, but this has a price you have to pay, of course. And if you look at design evaluation and then estimation efficiency, for instance, so here you see the fractional increase in the confidence interval length for testing these terms, estimating these terms. And this metric should be 0 if you have an ideal design. So for instance, an orthogonal d-optimal design would have 0s in these places. And if it's less ideal, then these values go up. So we see that there are some metrics for yaw angle and grill coverage, our easy to change factors, but the confidence interval increase is much higher for our hard to change factors. So the standard error gets much higher for these estimates. And this is even worse if you look and compare quadratic terms for easy to change and hard to change factors. And of course we get much more data for the easy to change factors, and they are completely randomized. And then the hard to change factors, which are arranged in so-called whole plots, there you don't get so many degrees of freedom to test them. The analysis for such a split plot experiment is a bit more complicated. So if I click on model, so this is the model script stored by the custom designer. And here I remove 3 responses. I just look at efficiency And we see this is a response surface model. But again, the runs are not completely independent. So we have the whole plots as a random effect. So this means we cannot use standard least squares estimation anymore, but we switch to a generalized least squares model. In this case, JMP uses RAML, restricted maximum likelihood, to estimate the parameters. And this is the output you get. And looking at the parameter estimates, we see the estimated estimates. But if you look at the standard error, you see that the standard error for hard to change factors is 3 times higher than for easy to change factors. And we also see that we have 31 degrees of freedom for the easy to change factors, but only 4 degrees of freedom for the hard to change factors. So less information there, but it's easier for us, maybe the only way to carry out this experiment. If you are interested to see the full demo of this case study, you can follow this link, and then there are several demos online recorded by Peter Goose, one of the co-authors of the book I mentioned. And here you see wind tunnel experiment, a split plot design, which can be watched online. Okay, these were the most important demos I wanted to give for teaching, and these are the basic ones, but they include a real-life, real-world tool, the custom designer, which is the universal one-stop shop for getting an optimal design in many different situations. I just want to mention a few advanced DOE approaches. So modern designs, of course, here we have the definitive screening design we have to mention. And there's an info kit which really explains what this is about. So this info kit is called Teaching Design of Experiments in Chemistry and explains the benefits of a definitive screening design by solving the same problem in 2 ways. First, use a 12-run custom design for screening plus 6 augmented runs for optimization using a response surface model. And then secondly, a single 13-run definitive screening design, which gives you the same information while saving almost a third of the total runs. And let me just show you some highlights by opening the design table we got from a definitive screening design. And we also have the yield, the response data filled in. So here, let me show you the distribution. So here we see a definitive screening design is a 3-level design. And this allows us to test for curvature per factor, not just detect if any curvature is there using center points, but we can find quadratic relationships for our factors. If we look at the DOE dialog and then the column map and correlations, so this is the really good news here. So not only the main effects are completely independent and not correlated, but also our main effects are not correlated at all with all 2-factor interactions. And the same holds for the quadratic terms. So there's much less uncertainty about what we learned from a definitive screening experiment than compared to other classical designs, maybe a Blackett-Berman design. And that's the other benefit, if the number of active effects is low, screening and optimization can collapse into a single step. And then the analysis is so easy, you can use the fit definitive screening design platform in JMP, fit definitive screening, that's the exact name, and this does everything for you. It does some screening for the main effects, it checks higher order effects. It gives you information about the complete model. So here we have 5 terms basically plus the intercept, and 1 term is quadratic for time and 1 interaction. And then here we also get a profiler, and we see the interaction between temperature and modifier, and we also see the quadratic effect for time. And again, the optimization can be done by jump, and these are the best settings maximizing our yield using a definitive screening design. Learn a lot with minimum effort, minimum number of runs. And there's a low number of effects active, so that's really a concept, effect sparsity, which applies in many situations. So we don't have much more time. So just to mention 2 special purpose designs, just as an example. So one is about a consumer study, a choice experiment, when you want to know what type of product or service your customers really like. And there's also an example in the documentation. There's a sample data set, laptop results, and then you can use this, and this is called a discrete choice experiment. You can get from DOE special purpose. You can get from consumer studies, choice, design, and then you use a conjoint analysis, or in JMP it's called a choice model, to analyze such designs. And then you can see what the benefit is. In this example, maybe using the utility profiler, you can see what the monetary value is if you increase the battery lifetime of a laptop, or the speed of a laptop. And here you can see what this means in pricing, and then you can estimate what a consumer would pay maybe for doubling the disk size of a laptop. And a totally different subject is the last one, deterministic computer experiments. So in a physical experiment, your process response is random. You model the signal and you want to eliminate the noise. A response in a computer experiment is simulated by simplified models of the real world, for instance, simulating climate changes. And this output is deterministic. So you don't need to worry about replication or randomization at all. And for these type of experiments, so you can use space filling designs in JMP, special purpose space filling. Let me add a 3rd continuous factor, and then you can choose from different approaches. In most cases, the Latin hypercube design is used, and then make the table. And then we see that here all the points where we test, all our test points are distributed equally over our design space, which has 3 dimensions in this case. And when you analyze such a design, so then you use a Gaussian process model, which can tell you which effects are active and not. So they go hand in hand. Space filling design, typically led in hypercube, but you have many more options in JMP. And then for analysis, the Gaussian process model, which is also available under the Analyze menu. Okay, so we are actually done. MISC is just mentioning some important things for augmenting designs and design diagnostics, and then, as I said, some tips for you to recap what we saw today and resources. And that's for my demo for now. And what's next is a follow-up email, so you get a link to the recording of this session and to download the journal. We sent you also a link to see what other webinars will be done during the spring of this year. And of course, we are always here to help you, academic@jump.com.